on this, and let's dive in. So exam number 2, it's the climate change exam, because that's what it's mostly on. So I'll just tell you guys that right now it's mostly climate change. I'd say it's about 80% climate change, well, maybe 75% climate change, then probably about 20% microplastics and waste, then a little bit of some other stuff. But again, it's mostly climate change because climate change is the most important issue that we discussed this semester, right? So it bears making sure that you guys all know all the stuff about climate change, because again, it is just so damn important. And so what's the exam format? Well, there's no essays, so you're not going to be getting any material. I'm not going to give you the essay questions ahead of time because there are no essays, none whatsoever. But there are 34 multiple choice questions. And so, I think it's about 15 more than the last exam. And there are 2 short answer questions. I'll tell you right now, one of them is on climate change and the other one's on microplastics. So just letting you know right now, those are the 2 short answer questions. The short answer questions have 3 to 5 parts to them. So you'll be answering multiple things about climate change and multiple things about plastics. But part of the reason I sort of switched up this format is while I like the essay questions, and I have some pretty cool essay questions written for some climate change stuff. The problem is actually my grades are due Sunday. So if all of you waited till Friday to do your exam, that means I'd have to grade your class and my other section of this class in 2 days. So, and that's really hard when I'm trying to read essays and stuff like that. So I went with the shorter format. I'm sure you guys all are so saddened by that shorter format. But that's where we're going. So multiple choice and short answer. And again, it's mostly on climate change, which is what you'll see from these slides. And there is a time limit here. So it's just like the last time, it's 2 hours. If you do need accommodations, and you just got to let me know, because otherwise I'm going to forget to do it. But if you send me an email and be like, hey, I have accommodations, you don't need to send me the stuff again, like the documentation or anything like that. But just so I remember, because I'm prone to forgetting things like that. So that's just who I am. So, but that's where we're at. So climate change, microplastics, waste, and a little bit of air pollution and water pollution. So that's really what we're going to be focusing on today. So it is 2 hours. It is supposed to be done in one sitting. So you have to do it in one sitting. So you can't start it tomorrow and finish it Friday. Got to sit down very much like the first one and do it. It will auto-complete on you if you do not finish it within the 2 hours. And I know that's kind of, I don't know, maybe a scary thought. I don't know. But if you have any problems with, technical issues or questions on the exam, definitely let me know. I'll try to answer them as fast as I can and solve them. But you don't need to worry about accidentally, not having enough time. I think 2 hours should be more than enough. But we shall see. So, all right, let's dive in. So the first sort of topic we'll talk about today is a refresher on the difference between climate and weather. And so the quote I always give my students is from Mark Twain, and I gave it to you guys as well. But Mark Twain says, climate is what you expect and weather is what you get. Now, what Mark Twain is referring to there is that climate is what we predict is going to happen based upon years and years and years of data from the weather, right? What is the weather supposed to look like in July? That's our climate. It's long-term patterns of weather. But what does weather really encompass? It is short-term patterns, but it encompasses all the things you think about when you pop on the weather channel, or you hop on the your phone app, right? And it's wind, humidity, temperature, so on and so forth. So all those things really blend together to give us a weather. But again, our climate is what we expect that weather to look like over yearly to decadal periods. And so it's a pretty common mix-up among most people, which is why I always make sure everyone in my classes knows the difference between climate and weather, because you'll see someone every now and then go, it's snowing in June. Oh, climate change isn't real, right? That's just not what climate change is about, right? Climate change is about long-term patterns, right? It's not about changes in weather, though certainly weather is encompassed within climate, but it's about long-term trajectories. And again, this is our weather of map of weather and our map of climate, right? Consistently hot in this region of the world, in the American Southwest. That's the climate of the region. Consistently cold in, middle of nowhere Canada up here, right? So that's what we expect. Now, the biggest aspect of climate change is what we are doing to our atmosphere. Now, remember the atmosphere, and it's kind of weird to think about it this way, but it's really all it is. It's just a giant pile of gas suspended over your head. It's really all it is, right? And that atmosphere is pretty dang consistent across the planet. There are like hotspots, like where you have more CO2 in, say, a city, but generally speaking, the atmosphere is pretty dang consistent across the planet, which is a pretty cool thing when you think about how big the planet is and, how crazy humans are with our activities. But the atmosphere is comprised primarily, and I say primarily, I mean 99% of nitrogen and oxygen. So those are the two big boys. Nitrogen basically does nothing, and oxygen is the gas that you know and love because you breathe it in every day. Right? It's kind of an important one, right? Now, there are what we call trace gases out there. Now, those trace gases are primarily argon. Argon is about 0.9 to 0.8% of the remaining atmosphere. And then we have CO2, methane, nitrous oxide, and all those other gases that make up that less than 0.1%. So the atmosphere is very, very simple, which is good for atmospheric scientists. But again, it's super duper important. Now, an important aspect of our atmosphere is it has different layers, right? So we live in the troposphere, which is the lowest region of the atmosphere. That's where all the weather happens, that's where all our buildings are, that's where Mount Everest is, right? So all the things we know about Earth reside in the bottommost layer. But then we move up to the stratosphere, which is the next highest layer after our sort of basal layer of the troposphere. And within the stratosphere, we have the ever important ozone layer. Now, from a history standpoint, and this doesn't really matter for the exam, but I didn't make mention of it in the class when I talked about the ozone layer, so I just wanted to make mention of it. Prehistoric Earth, before about 1.5 billion years ago, when oxygen-based photosynthesis evolved, there was no ozone layer. So all the Earth's sort of organisms were confined to the ocean. Now, why was that the case? Well, the ozone layer simply acts as a mechanism to protect us against ultraviolet light. Now, you guys probably know this, and we've sort of talked about this, but ultraviolet light is a mutagen, right? It damages your DNA. And anything that's a mutagen that can damage your DNA can do a couple different things. So it can make you get a sweet tan. That's just one thing, damages to your cells and your DNA can do. It can give you cancer, right? That's all cancer really is, right? Damages to your DNA, which gives you tumors and all the associated things about cancer. And the other thing it can do is give you sunburns, right? Cause your skin to kill itself, which is all sunburn really is, which is the most crazy way to think about what a sunburn is. So UV light is no joke, but our ozone layer takes one for the team, basically, right? It absorbs the most UV light, in particular the most damaging of UV lights from the sun, and protects us, allowing life to exist on the surface, not being confined to the ocean as it used to be in prehistoric times. Now, like most things on this planet, we've decided that we wanted to give the middle finger to the ozone layer, because why wouldn't we? Because that's kind of just what humans do, right? And this started actually sort of around the 1940s, i.e. the advent of refrigeration and air conditioners, because our old school refrigerators and air conditioners were chock full of gases called chlorofluorocarbons, which are simply called CFCs. You don't need to remember what they are or anything like that, but those are the bad boy gases, and they were found in spades in our cooling equipment. They're really great for helping cool. Don't get me wrong. They're like asbestos, right? Asbestos is a great fire retardant, but asbestos is really bad for human health, right? It causes cancers and mesothelioma, that specific type of cancer associated with asbestos. So CFCs like asbestos are great, but they're really bad. And in particular, CFCs are bad because they get into the atmosphere and they hang around the stratosphere, and they basically fight and kill our ozone, which is a bad thing, right? Damage to our ozone layer means more UV light gets to our planet, which means more likely to be exposed to more UV light, which is clearly a bad thing. Now, the reality is this ozone damage occurs pretty commonly across the planet, but it is heavily concentrated over the Antarctic, which is why we always sort of look at maps like this, where the Earth is basically turned on its butt, right? We're looking at the Antarctic and the Antarctic Peninsula here, right? So you can see the total ozone, lower levels, lower colors, I should say, mean bigger holes, right? So less ozone. And you notice that our ozone layer had a pretty big hole in the 90s, and it kind of recovered over time. And then it sort of reached its minimum in 2002, right? And then it's kind of come roaring back, where we're seeing a pretty heavy depletion of ozone in modern times. Now, what stopped ozone from really being destroyed over the Antarctic in 2002? Well, about 15 years prior to that, we enacted the Montreal Protocol. I recommend you read about it because it is one of the most successful pieces of global environmental regulation that we've ever seen, which is not something we're really good at. We're not really good at doing global things, right? I mean, probably the last great global thing outside the Montreal Protocol was probably like the eradication of smallpox. But that's just my opinion, of course. And we have the Montreal Protocol, and it's set to ban CFCs globally. Pretty much every country signed up onto it. And as you can see, the Montreal Protocol worked pretty well. But as we'll discuss in a few slides, the ozone hole came rearing back in after 2002. In particular, it started to come back pretty heavily in modern times. And that's going to be due to one of our greenhouse gases, our lovable friend, nitrous oxide. So don't forget about the ozone layer. It's a really important layer. It does not contribute to climate change at all, remember. It just simply helps protect us from ultraviolet light. Now, we took an 800,000 year look at climate, and climate is in terms of temperature and CO2. And part of that was looking at how variable Earth's climate is, right? Earth's climate is not stable, not by any means. But the reality is the cycles that change Earth's climate act over periods that we simply are not able to observe in a human lifetime, or even sort of the modern view of what is happening to Earth's climate. And so we talked for a bit about Milankovitch cycles. Now, Milankovitch cycles vary between 26,000 and 100,000 year cycles, where we basically see changes in the Earth's behavior, either its orbit. So as you recall, the Earth is currently in an egg-shaped orbit, but it can switch every 100,000 years to be in more of a circular orbit. We have the obliquity, which is changes in the angle of the Earth, and we're at 23.5 right now, so right smack dab in the middle. But remember, what causes the different climate on Earth is how much direct sunlight the Earth gets. And so changing the obliquity or changing the eccentricity, or sort of finally changing the sort of the wobble or the precession, also all augment how much direct sunlight the planet gets, thus leading to warmer temperatures or potentially colder temperatures in different parts of the world. So Milankovitch cycles, they are pretty cool. Thinking about how a huge celestial body changes its behavior. It's kind of a crazy thing to think about, in my opinion, but they do, again, naturally affect Earth's climate. So that's three aspects, these sort of three major shifts in the Earth's behavior. Then we have, and I don't have the slide for it, but I will just make mention that we do have changes in sunspot cycles every 11 years. So those occur, but I didn't bring the slide for it because you don't need to worry about it for your exam. I would just think about these couple. Then we have El Nino and La Nina, just to sort of reiterate what those are. Remember La Nina. Apparently I forget my Spanish, because apparently I just do those things. La Nina is sort of business as usual, where we have westerly winds pulling hot water and hot air off the Central and South America, causing it to pool in a specific spot in the Pacific Ocean off the coast of, New Zealand and all those fun islands just south of China. But then we have El Nino, which is the not so fun brother of La Nina, where those westerly winds shut down, causing most of the Pacific Ocean to heat up, and including causing a massive piling up of hot water and hot air on the coast of Central and South America. And remember, the Pacific Ocean is about 30% of all the ocean water on the planet. That's how big the Pacific Ocean is. I think it gets lost when you look at pictures like this, but the Pacific Ocean is enormous. Like, it is huge. So a meaningful change in the temperature of the Pacific Ocean leads to pretty serious changes in Earth's climate. In particular, when El Nino happens, it makes the rest of the world really, really hot. And I mean really, really hot by about 2 degrees warmer. So El Nino and La Nina, two important weather, or I should say climate phenomena. They act on decades or years. They alter weather patterns for about 1 to 2 years, and they last for a decent chunk of time, but they eventually do go away. So those are sort of the most important ways we change your climate. And then the final one I'll make mention of is our volcanoes, where we can sort of see the effect of them just nicely in this map, where we have 1750 to 2000. Average land temperature, and you'll notice that we kind of are hanging around, and then we have these precipitous drops due to volcanic eruptions. Why is that? Well, remember, volcanic eruptions occur, they produce sulfur dioxide, so this gas called SO2, leading to increase in the Earth's albedo, i.e. we reflect more solar radiation back into space when there's a volcanic eruption, thus cooling the planet. But very much like El Nino, it's a short term, right? This only lasts for a few years before the temperature of the planet bounces back. And so we have these two very, very short-term alterations to Earth climate, volcanism, as well as La Nina and El Nino. And then we have more long-term changes. And I would recommend that you definitely read up on one of these 3 slides, just to make sure you know what Milankovitch cycles are, or what El Nino is, or what volcanism is. Just make sure you know at least one of those. And clearly, I'm telling you that because there's probably a question on the exam about it. And I say probably, I mean there is one. So spoilers. And so there are natural variability in the Earth's climate. That is 100% true. But if you did not watch this video, I would definitely watch this video, because it really puts in perspective and sort of illustrates very nicely about how dramatic the rise in CO2 is in modern times. And this video does great, but there's lots of other ways you can look at this. So this graph here, remember, where we looked at about a 10 part per million increase in CO2. This is at Hawaii, but remember the atmosphere is pretty consistent. So at Hawaii, we're seeing a 10 parts per million increase in only 4 years or so, 4 to 5 years. So we're seeing a dramatic increase, 10 parts per million. And if you sort of think about that in perspective of global history of CO2, remember, to go 10 parts per million, historically speaking, it takes hundreds of thousands of years to make meaningful changes in CO2, but we're seeing changes in CO2 in 150 years or so that rival what we would only see, and again, in like 50,000 year periods. So the key thing for climate change is, yeah, of course, it happens naturally. The Earth's climate is dynamic. It changes, and it changes over space, and it changes over time. But the key here is the slope of this line. It is faster than it has ever been. And that's the key. That's the key. It's faster than it's ever been. And there's no way, not volcanoes, not El Nino, not Milankovitch cycles, not sunspot cycles, there's nothing on this planet that can explain this rapid rise in global carbon dioxide and global temperature outside of human activities. And that's the key. If you take nothing away from the climate change lectures, that is the most important thing. Because that's sort of the answer to any climate skepticism, it's how fast it is, right? And that's just unprecedented. If you took humans away from the equation, this cannot happen. Nature does not simply change that fast. Climate does not change that fast. So we talked about the greenhouse effect, and we talked about what that does. Now, remember, the greenhouse effect is a natural phenomena. We have these gases, they're called greenhouse gases. Now, natural greenhouse gases, well, they're all pretty much natural greenhouse gases, except for the ones that humans make, of course. But these greenhouse gases normally are comprised of mostly water vapor, CO2, and then there's some other ones, methane and nitrous oxide. And remember, these greenhouse gases basically act as like a nice warm blanket, right? You picture like putting a colossal blanket over planet Earth, which kind of sounds weird to think about, but that's really what's happening. And that blanket, while it doesn't trap all the heat the Earth is sort of radiating off, remember, it traps a decent chunk of that heat, making the planet habitable, making the planet about 60 degrees warmer, 60 degrees Fahrenheit, of course, than it normally would be. So that's really what the greenhouse effect did. It's kind of like that warm blanket. And as you put more and more blankets on you, that would be akin to putting more and more greenhouse gases into your atmosphere, right? And so that's our natural greenhouse effect. But remember, humans are the one pushing on it, and we're pushing on it pretty damn hard. And we're doing it by adding primarily carbon dioxide. Remember, carbon dioxide is the resultage of the combustion of fossil fuels, right? Coal, oil, and technically natural gas, though natural gas, remember, can be made by bacteria, microbes in the soil. But things that are long dead organisms, right? Things that we dig up from the ground, things that don't renew on a human life scale, that we burn them and they produce precipitous amounts of CO2. And remember, that burning ties directly to our activities, right? The more active humans are, the more energy we expend, the more of these greenhouse gases we put in the atmosphere. So carbon dioxide is the big boy, he's the bad boy. Methane and nitrous oxide are number 1 and 2, and we'll talk about these again and their sources and stuff like that. But the important sort of thing about these greenhouse gases is, yeah, they're natural, but you sort of can look at this history of CO2, right? So I think this is a great example. You can look at sort of the flat line of Earth's population. It's kind of slightly increasing, but it doesn't really take off to the 1850s. But you look at CO2, it's hovered around 280 parts per million, basically for the a huge chunk of recorded human history, right? You're talking about through the Renaissance and through the Bronze Age and all that stuff. And you sort of have this pretty, the pyramids being constructed, of course, sort of cool stuff like that, right? And you sort of see it's really consistent. And then when human population takes off, you see CO2, nitrous oxide, and methane. Ignore the red line. We won't talk about that one. All dramatically expand. Now, why are they expanding? Well, remember, in the 1800s, we saw that kick in, or 1700s technically, but around 1800, we saw the mass sort of adoption of the Industrial Revolution, right? And principally the burning of coal. And remember, the burning of coal produces lots of CO2. And so we're seeing the rise of human population, that consistent J curve that we talked about for exponential growth. And with that exponential growth of humans, saw the expansion of technology, saw the expansion of modern agricultural practices, and so on and so forth, leading to the rise and the rapid rise of these. And remember, just sort of think about this time frame, right? CO2 from 1800 goes from 280 to well over 300 by the year 2000. But think about that in the context, that's 150 years. If you look at the previous 1800 years, CO2 barely moves by a few parts per million. So again, the rapid rise is the key here. And remember, as this goes up, so does temperature. And so CO2, as I mentioned, is mostly from greenhouse gases, but remember there are other sources of CO2. We talked about wildfires, and I showed you this awesome meme of Michael Scott. So CO2 is produced precipitously from wildfires. And so those are sort of the main sources. We also talked about cement, right? Cement is a great source of CO2, but you don't really need to remember anything about cement for the exam, so I didn't put it on the slides. Then we talked about methane. Now remember, methane is naturally produced. It's made by soil microorganisms. There's also soil microorganisms that eat it, which is kind of a cool thing. I had a friend that used to work on that idea. She gave up after a while because it was really hard to work on, but it is what it is. But remember, the vast majority of our methane comes from our cows. Now remember, our cows, they do not fart out methane, as this oh so funny comic will tell you. They burp methane out. Now, why is that? Well, these cows have these methane producing microorganisms in their gut, which leads them, as they eat food, to produce a little bit of methane. And of course, very much like us, as we produce gas, we have to expel that gas, right? Burps, or sometimes farts. But in the case of methane, it's cow burps. Other major sources of methane include natural gas and pipeline leakages from coal mines, wet rice paddies, and then finally landfills, in particular food waste. So as we discussed, food waste is a huge problem, not just from a perspective of waste management, or financially, right? Remember, financially, we waste what, $150 billion a year as Americans on food waste. So it's a huge chunk of change. It's a huge problem in terms of management of waste. But from a climate change perspective, remember, once we throw food away, remember, food just doesn't just like kind of hang there like plastic does, right? Food breaks down. And what breaks food down? Well, it's critters, right? Microbes, fungus, maybe rats that make it in. And all those things produce carbon dioxide or potentially methane. And so as we discussed, if you summed up all the CO2 and methane emissions from food waste across the entire planet, it'd be the third largest country in terms of greenhouse gas emissions, more than India, which and Russia and Japan combined, which have a population of what, 1.4 billion combined, right? So huge amounts of people in some of these other top countries, but again, still don't produce as much greenhouse gas as just food waste. So remember, food waste is a big deal. Like, it really is a big deal. And it's not just a big deal, again, for the economy or climate change, but remember, there's a huge number of food insecure people on this planet. So food waste is, well, it kind of sucks. That's all I really have to say. So let's move on to our final greenhouse gas, and this is going to be our buddy nitrous oxide. Now remember, nitrous oxide can be produced from the combustion of fossil fuels. That's about 10 to 12%, depending on who you ask, and depending on where you are, of course. But the vast majority, it comes from our modern agricultural system, that horrendous way we grow food, right? That incredibly destructive way that we grow food. And so the way we manage our fields produces the vast majority of our nitrous oxide. And so remember, nitrous oxide is one of the more concerning greenhouse gases, because it is not only the most potent greenhouse gas that we make in large quantities, of course, but remember, it also depletes our ozone layer. Right? Nitrous oxide reacts with ozone, depleting our ozone layer. And so as you sort of saw from the Montreal Protocol slide, remember, our ozone layer is going away still. Why is that? Because we're producing more nitrous oxide than we ever have before. And that's principally due to the way the United States farms our food, spreading to other parts of the world, in particular, how active it's being in places like India and China, which have massive, massive populations. So nitrous oxide is a bad boy on two different levels: ozone and climate change. And so this brings us to the temperature anomaly today. All these greenhouse gases that are building up precipitously in our atmosphere are leading to about our planet being 1.02 degrees centigrade warmer than industrial time, so before the 1850s. And this leads to warming globally. Now, globally, if you take the average temperature, we're about that. But as this map really illustrates from our friends at NOAA, it's not uniform, right? Some places are cooling, and those are few and far in between, right? Oops, I jumped the gun there. There's some spots, right? Here, 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 and here. But most of the planet is on fire in some shade of red or some shade of yellow, which is slight warming or potentially slight cooling, depending on the shade. But again, most of the planet is pretty deeply red. And in particular, places that are heavy population centers are seeing some pretty heavy increases, and some pretty dry and some historically very cold places are seeing some pretty heavy increases, right? So lots of heat increases in Africa and the Middle East, which have not only a lot of people, but are also historically very dry. We're seeing huge increases in temperature here in the Northeast and along the Eastern seaboard, where there are lots of people. Certainly lots of people over here in this neck of the woods. Places like Australia that are historically very dry as well are getting warmer. And then we're seeing large increases in the Arctic. The Arctic is basically on fire in terms of heating. And so we see this dynamic change in global temperature. So we know that it has risen by about 1.02 degrees, but it's not uniform. And that shouldn't really be all that surprising, right? When we talked about weather, when we talked about, cycles of water on this planet, right? That shouldn't overly be surprising to you guys at this point, right? The planet is dynamic. And so what happens here might affect what happens here, but usually they're kind of on their own little sort of different things. So, but we are warmer globally. And that's one of the other key takeaways from here, how fast it's happening and that it's leading to an overall warmer temperature. So we discussed lots of aspects of what more carbon dioxide, what climate change means for our planet. And I gave you about 40 something slides, give or take a few slides, course, about those effects. And they range from disease to pests to food insecurity to food changes in nutrition, all sorts of things. But I'm just going to talk about two today because, well, they're direct questions on the exam. So that's why we're going to talk about them. And so first is ocean acidification. Now, remember, when you dissolve CO2 into the ocean or any body of water for that matter, The carbon dioxide reacts with water and produces a weak acid called carbonic acid, which lowers the pH of the ocean slightly. Now, when you hear sort of slightly, that makes you think, oh, it's not that big a deal, but a subtle change in pH is a big deal for the ocean, just as a note. I won't go into why that is, but just know small changes in pH are huge for the ocean. And this leads to some pretty severe consequences for things with shells. So lobsters, mussels, oysters, snails, anything with a shell that's hard, they don't do so well under high CO2, because as things get more acidic, it leads to damaged and weakened shells, which leads to potentially the decimation of entire species. In particular, we're seeing that, oops, wrong way. We're seeing that pretty heavily in our coral reefs. You guys probably see in the news every now and then about X percentage of the Great Barrier Reef in Australia is bleached. Well, under higher CO2, as well as warmer waters, our coral reefs become stressed, they become bleached, and they eventually die. And coral reefs, remember, this coral is not just a rock, it's not just a plant, it is a living animal. And so when this animal dies, it's basically like the functional equivalent of like a skeleton, like not a skeleton, but like a decomposing corpse hanging around in the ocean. So like picture if like, you died and you just laid around. That would be like what a dead coral is. Because remember, corals they're not rocks, they're not plants, they're animals. So when this happens, the coral reefs are done. They take decades and decades to come back. And so those are sort of the effects of more CO2. There's lots of effects of CO2, but I'm talking about acidification in particular because it's a question. So just as a note. And then we talked about sea level rise. Global oceans are expanding, and they're expanding relatively rapidly. And so this graph does it well. This graph also does it pretty well too, where we have some changes in sea level. Some places are getting shallower, but most places are getting deeper. Now, why is that? Well, remember, global oceans are rising because of two factors. The first being thermal expansion of water. As water gets warmer, as water gets warmer, it expands in volume. That's just what water does. Actually, that's what everything does for that matter, but water does it as well. But the bigger sort of issue here is actually the melting of glaciers and melting of landlocked ice. So ice that is hanging around on land. And so this is primarily in places like Greenland and Canada and Russia and places that are high up, where we're seeing just as a reminder, right? We're seeing pretty heavy warming in places where there's glaciers and ice trapped on land. And that's leading to lots of meltwater, which is leading to higher levels of the ocean. And you might think, well, is there really enough sort of glacial water out there to cause meaningful changes in the ocean? And just to go back to this graph, Greenland is monstrous, and Greenland is one giant piece of ice. So yes, there is lots and lots of landlocked ice out there that if melted will increase the volume of our seas. And that's a big deal, in particular for places like the eastern seaboard of the United States, where we're seeing some of the fastest rates of sea level rise on the planet, where lots of people live, or potentially in these islands over here, right, where lots of people live, lots and lots of sea level rise. So that's our sea level rise. So those are the sort of the two ones you're getting asked direct questions on. However, and I would write this down because I think it's important. There is a question, one part of your short answer question, of course, that asks you about some of the effects of sea level rise on, I'm sorry, not sea level rise, of climate change on a specific aspect of your choosing, of course, on your future. So what I would recommend is I would ignore these slides about sea level rise and ocean acidification, and I would learn pretty in depth one of the other effects of CO2 and climate change, of course, that we expect to see in the future. So just letting you guys know that. Choose a topic that we know climate change is going to change going forward. Know that really well. Take some notes on it because you're going to need it for one of the short answer questions. So that's like my version of giving you the question beforehand, but without actually giving you the question beforehand, of course. So that's climate change. Those are sort of the important things. The only thing that I actually realized now that I didn't actually put in here for a slide is actually the albedo. I sort of mentioned the albedo when I talked about volcanoes, but just to let you know, you should probably look at the slides on albedo. Again, I'm sorry, I realize now that I forgot the slides for albedo, but you should definitely look at albedo. just as a note. So this brings us to waste. So we talked about two distinct types of waste. We talked about hazardous waste and solid waste, and wrapped within both of those is plastic. So we'll talk about waste, then we'll talk about plastic, and then we'll talk about pollution, and then we'll be done. So which is nice. So we talked about waste to detoxify hazardous waste. Now remember, we define hazardous waste as anything that's hazardous because it's chemically reactive, explosive, flammable, and it can harm life on the planet in some way, shape, or form. That's what hazardous waste really means. And there's multiple ways to clean it up. Bioremediation, where we use microbes, phytoremediation, where we use plants, or we do what the cool thing that the US Navy does in plasma gasification it, basically incinerating it into a fine ash, which is pretty cool. We can also break it down physically with resin or charcoal. We can also chemically convert it into a less harmful chemical. But remember, the most common thing we do with hazardous waste is we bury it. And why is that? It's cheap and easy, right? It's easy to dig a hole and dump some hazardous waste in the ground, right? That's sort of the lesson about waste, right? What do we do with waste? What's the cheapest thing? We do that. And so land burial is by far the most common and the cheapest way to handle waste. But there are other ways that are also cheap. This includes surface impoundments. Remember, surface impoundments are just giant, or sometimes giant, but usually relatively small little ponds that people dump toxic waste in, hazardous waste, things like that. And they just kind of let it sit there for a while, and they don't really do anything about it. And very much like burying waste, remember, surface impoundments is an imperfect method for storing waste, right? It has a high probability of getting into the environment, which is bad. And then the best thing to do with hazardous waste is to store it, not like this, of course, but taking one of these drums that's nice and brand new and storing your hazardous waste in it. So for instance, our nuclear waste here in the United States and abroad, and I say abroad as in like other countries, they have these drums. They're specifically lined with lead. They put nuclear waste, which is a type of hazardous waste, into these drums, cap them off, and store them in secure vaults so that they don't get out into the environment. But remember, this is expensive, like very expensive. Like I feel like this is prohibitively expensive at this point in time for most of our hazardous waste, because again, it requires an investment of metal. It requires an investment of burying it or storing it somewhere, and it requires investment to monitoring it. All things that businesses simply don't like to do. And this brings us to solid waste, which encompasses hazardous waste. Remember, all hazardous waste is solid waste, but not all solid waste is hazardous waste. And hazardous solid waste is gas, liquid, or solids, and it ranges from municipal solid waste, i.e., you throw out a container of Cheetos or something like that, to toxic waste like nuclear waste. So there's lots of things that fall under the compass of solid waste. But it's sort of one of the other key takeaways about solid waste is, remember, the way we handle our waste is not sustainable, right? That's sort of the thing you really need to take away most from our waste protocols at this point, is it's simply not sustainable. And then I gave you some numbers about the craziness of the waste, right? United States is #1 in total waste and waste per capita. And so this is one of the things we're #1 in that really stinks to be #1 in. But it is astronomical amounts of waste that we produced. And then we talked about a little bit about these, the contribution of waste infrastructure, in particular outdated infrastructure, on waste getting out into the environment. And one of the things we talked about was these combined sewage outflows. I'm not going to dive too much into these, but I would definitely recommend just sort of reading this slide about CSOs and becoming a little bit familiar with these CSOs. So outdated infrastructure that leads to waste, both hazardous and solid waste, making it out into the environment, which is clearly not good. And then we talked about one particular type of waste, and this is plastics. In particular, we talked about what happens with plastics in relation to human health and plastics in relationship to how they affect the marine environment. And so we talked about organisms that live in the ocean. They oftentimes run into plastics on accident, right? You see a fish swimming into this plastic here, right? Leading to it being like essentially choked off by plastic, right? That's an accident. Or this turtle accidentally sucking in plastic, or the sea lion accidentally getting stuck in fishing gear. So they can accidentally run into them, as you sort of see here too, or sometimes they accidentally ingest them while they're trying to get their own food. And so the sea lion might have thought this was a prey and it tried to eat it, and it got the bag stuck on its head. Or we can look at the contents of the sperm whale's gut, and we can see it's just chock full of things. And again, it saw something that it thought might be food, and it tried to eat it. and it didn't know any better, right? It doesn't know this is plastic. It doesn't know this was going to kill it, right? And so accidental ingestment is pretty dang common for animals, but again, it's all about accidentally associating with things that are supposed to be natural. So remember, we produce astronomical amounts of plastic on a year-to-year basis, hundreds of millions of tons. And remember, a huge proportion of that plastic makes it into the ocean. And principally, remember, most of our plastic makes it into the ocean from Asia as well as Africa, though the United States does round out the top 20, as does Brazil. So it makes it in through two key parts of the world, but remember, most of our plastic makes it into the ocean, not so much by people directly dumping into the ocean, but mostly by rivers. And in terms of total overall mass, remember, China does lead the way in mismanaged plastic waste globally, followed by a myriad of countries, again, mostly found in Africa as well as in Asia. And so why do we care about these plastics? Well, I showed you those terrible images earlier, right? Of, organisms being stuck in plastic or choked by plastic or stomach full of plastic. But remember, plastic has a myriad of effects, right? And it's not just like I ate a lot of plastic, which means I can't consume as much food as I need. It doesn't affect my capability to reproduce, doesn't damage my internal compartments, or reduce my overall growth, right? Those are just like, I ate plastic and they affected this biology aspect of me. But remember, lots of things can stick to plastic, and they range from heavy metals to hormone mimickers, to pharmaceuticals, and pesticides, and things like asbestos. They bind, and those things are toxic, right? You guys know lead is toxic, cadmium is toxic, caffeine, and acetaminophen, which might not seem toxic to you. Remember, caffeine and acetaminophen actually evolved as defense mechanisms against organisms. So they are toxic to most organisms on the planet. We just use them for fun stuff, right? Caffeine for productivity and acetaminophen to get rid of our headaches, right? And so they have direct effects, i.e. I consume them and they hurt me some way directly, or there's a poison pill attached to our plastics. So it's kind of a mixed bag, right? They can directly harm you, or they can give you a toxic dose of lead and that can harm you too. So, and remember, it's not just like natural organisms too, right? It's things we care about, right? Our tunas of the world, our oysters, our clams, our mussels, right? Lots of things are ingesting plastic, and in turn are also ingesting these things that stick to plastic, which is concerning from a human standpoint, is because if those things happen as something living in the water, pretend we're talking about a salmon, and is absorbing more and more and more things that stick to plastics from the environment, those are going to accumulate or bioaccumulate in that salmon over time. But remember, as we go up the food chain, it becomes more magnified, because as we go up the food chain, remember, you have to eat more and more of the things below you. So if you want to sort of get a good idea of biomagnification and what it looks like, that table you did for your lab is a great way to sort of think about it mathematically, right? You could plot that, right? And you could see that it starts off low at the bottom of the food chain, as you see here, but ramps up to really, really high levels by the time you get to the top of the food chain, right? I'm sure you guys saw that number you got for your orca in that lab was huge, right? It was billions. It's huge. And so biomagnification really concentrates things. And remember, from a human standpoint, this is one of the more concerning things. I mean, clearly it's bad for the organisms, but from a human health perspective, we eat at the top of the food chain, right? We eat salmon. We eat a lot of salmon. And so our salmon have lots of things that are associated with plastic, like metals and BPA and so on and so forth. That means we're more likely to ingest those things. So it's kind of a bad thing. But again, it's also a bad thing for our marine friends, which led us to talking about what happens to humans. Now, you guys had that documentary to watch. It talked about how it affects male fertility. Because a lot of the things that we put in plastics mimic hormones, right? You guys saw it. They talked about BPA, bisphenol A. It acts like a hormone, and hormones, remember, do everything. And so if you mess up your hormones, you can severely impact development. But there's lots of things that plastics affect. And remember, our certainty about the effects of plastic on the at larger scales is a little bit unknown at this point, but most of the anecdotal evidence that we have right now, which there is quite a bit of, is pointing towards plastics being a huge public health crisis going forward. So remember, the on the scale of 0 is not certain at all, and to 1 is being 100% certain, we're edging towards being 1 on that scale in terms of the effects of plastics on human health. And remember, there's lots of things that these are been shown to do, whether it's growth or metabolism related, reproduction, as you saw in the documentary, effects with development, serious conditions like ADHD or autism, and then lots of other very serious health issues, diabetes, insulin resistance, cancers, obesities, things that either kill you slowly or kill you over the long term, right? Or damage your body over the long term. So lots of associations between plastics and health. And so the key takeaways from the waste lab is the waste aspect is we're really bad at it. And that leads to the plastics problem, right? Not just in the environment, but also in our own bodies, right? And so the problem is, remember, it's huge in scale, right? It's a global problem, very much like climate changes, right? And so it's this huge problem. It crosses borders, and so it really requires pretty massive changes to sort of fix it. But the key is, it's not something that we can stop overnight, but it does take some level of investment to sort of stop. So, and then we get to the final things that you really want to consider, and that's pollution. You'll remember we talked about these things during the water and air class. This was earlier in the semester. I've held back from putting these on exam till now because they really fit with climate change the best. In plastics as the best. So the first thing we'll talk about is point source versus non-point sources of pollution. And so remember, a point source was like Minamata, right? They had a factory, it was producing some toxic byproduct, it flowed out through a pipe into the ocean, and that was a point source pollution because we know exactly where it's coming from. And that's in contrast to, say, something like runoff from a forest or runoff from a series of farms, right, where there's multiple inputs to the waterways or into the air, of course, and all those things make it out to the end. And so we're seeing an effect of pollution down here, but we're not sure where that pollution comes from, thus making it a non-point source of pollution. But again, if we had a problem with mercury and we only have one factory that produces mercury, well, it's the factory's fault, right? This led us to talking about atmospheric pollution. Now, remember, atmospheric pollution is the addition of any material that can affect human health or organisms. And there's so much things that fall under air pollution, like so many things. And it's like hair, it's dust, it's pollen, it's volcanic ash, it's ash from fires, soot from the combustion of fossil fuels, even sea salt. Lots of things are pollutants. All they have to do is cause some form of harm to the environment or to the organisms. And that's really all that encompasses pollution, which is kind of nice. Now, the final thing we'll talk about is there's just two distinct types of pollution, right? There's primary pollutants, i.e. substances that are emitted or produced that are directly harmful. And these include things like hair, products from combustion, dust, pollen, mold, beach sand, salt, anything that is directly emitted from a source and it's directly harmful. That's a primary air pollutant. And then we have secondary pollutants, things that are emitted, changed when they make it into the atmosphere, and become something else. And so the example I gave you is smog, where we mix together smoke and fog together. We have a reaction that occurs in the smog, making it a secondary pollutant. So because we're changing that primary pollutant, i.e. the combustion products, combustion products from in a car or something like that, it causes it to change a little bit, thus becoming a secondary pollutant. So you just want to make sure you know the difference between a primary and secondary pollutant. That's really it. You don't need to remember the examples or anything like that, but just remember that we have two distinct types of pollutants and what's the difference between them. And then the sort of final thing I mentioned is just sort of remember the difference between point source and non-point source solution. Point source pollutions. I don't know why I like to combine them. I don't know what it is when I talk about pollution. I don't know what it is, but just remember the difference between these two. But other than that, that's going to be it. So those 43 slides, outside of the albedo slides, which I'm sorry, I forgot to add, are really all you need to know. But again, you have 2 hours to do this exam. It's mostly multiple choice, and I gave you a pretty big hint about what to expect for your short answer question on climate change. So that's going to be it for the exam. So I'm going to stop recording this because you don't really need to